Okay, is everybody have finished the quiz? Okay, welcome back. Hope everybody had a good Labor Day weekend break. So today's lecture, we're gonna talk about the scattering on a more sophisticated level. We talk about from electrons, atoms, and today's lecture, my goal is to talk about what happens in, let's say, in a particle or your molecular in a polymer, okay, in a general sense. So before we start today's lecture, let's go through some of the quiz. I, together with my TA, graded the homework, and I think that overall, I feel there's some confusion for the part 3, and 1 and 2 are typically has done pretty well. Okay, so let's go through how do we generate X-ray. That is pretty simple, right? In the lab source, we generate by using accelerated electrons to hit a metal target. And then you can generate those X-rays. Or you can go to synchrotron using their X-ray sources, which is much more powerful. The second one, what is X-ray energy generated at USN? This is quite important. We talked about we are using a lab source. So in that sense, we are using an X-ray characteristic to copper K alpha line, which is about 8.04 keV, which translates to a wavelength about 1.54 angstrom. Okay, that's the length scale of the X-ray if it makes a photon. 1.54 angstrom, quite little. The other part is what is typical penetration depth in millimeter for polymer using this? So the penetration depth is just telling you how much X-ray can penetrate, right? So if you do a calculation, there is no solid definition of penetration depth. I should ask a slightly different, because if you penetrate, is it mean 10% of X-ray pass or 50%? So next time I should probably ask you guys how much attenuation length for 50% X-ray. But that's about a few millimeter. Some of you said few microns, and that's totally off. But think about that. When you do X-ray measurement, you want to prepare a sample of a few millimeter, okay? Ideally in a 1 or 2 millimeter range. Because of the electron density, polymer are generally lightweight elements made of carbon, hydrogen. So that's something you need to keep in your mind. If you prepare a polymer coupon that is a centimeter thick, you're not going to have the X-ray to pass it, okay? What is the influence of X-ray energy?
What would have been an acceptable answer in that case? Like a range.
Which one?
A range in millimeters.
Yeah, a few millimeter would be a good one.
Just the answer, a few millimeters?
Yeah.
Okay.
Sounds good. So the last one is about X-ray energy. It actually has two parts of influence. Start with the most simple one. We talk about penetration depths. That's something totally relevant. So if you increase X-ray energy, your X-ray has more penetration power. If you instead of use 8 keV, you use 20 keV, you can penetrate even very thin metal pieces like aluminums, etc. But using low energy, you wouldn't be able to do it. Vice versa, if you use 20 keV X-rays, you can penetrate now maybe a few centimeter polymer samples. There's a good website that I will post in the Canvas. You can actually do calculations how deep your X-ray can penetrate your sample. As long as you tell the software what is the depth, what's the density of your material, what's the thickness of your material, what's the X-ray energy, it will be able to tell you exactly how much X-ray can shoot through it, okay? Well?
A little unrelated, but for like question 2,
Mm-hmm.
do you need a homogeneous film to do it, or can you stack several films from the same film?
Yeah, you can stack films to do it. That's not a problem. But the pass means how much X-ray passes. It's something important. It doesn't care if there's air gap. Actually, air doesn't absorb that much. It absorbs a little bit, so you can certainly ignore it compared to polymer, right? So that comes down to example relevant is, what if I don't have a film, I have a powder? Then you need to roughly estimate what's the density, because that's important. If it's very loose, then you can go probably much thicker, just because the air doesn't absorb that much. When you're considering scattering, the absorption is something you need to consider for practical reason, okay? So there is also another portion hidden in this question is energy, of course, matters for absorption, but also matters for today's quiz, which is scattering vector Q. Because 4 pi sine theta divided by Q gives you scattering vector. So lambda, the longer the wavelengths, the smaller the scattering Q vector is, okay? So, you see that? So higher the higher the energy, you can measure much smaller features. So usually that's a minor effect, but just worthwhile to let everybody know this is also an influence, because lambda impact your scattering vector. So we're gonna come back to this quiz next time, okay? So let's revisit. I want to come back to this paragraph again. So in the last lecture, we talked about why X-ray, how X-ray interacted with a single electron. Is everybody recall? Electrons interact because each electron acts as relay antenna, so that you can broadcast X-ray in a different direction. So interference happens when you have multiple antennas has constructive or destructive effect, right? So today we actually going to go a little bit deeper into this. There's some equation involved, but I'll explain everybody. And I know the equations sometimes can be scary, but behold, and you can always ask me for questions. So we're going to explain how you come from a single electrons to be multiple electrons, and from multiple electrons to atom and a molecular. I don't think we're going to have time to go to polymer today, but we will try. A quick review here. The interference effect is the main reason why you have specific angle of scattering got intensified, okay? This is what we had a quiz today, scattering vector. Probably the most important concepts in the next few days. You need to understand what's the definition of this and how this Q is relevant to the scattering angle in length. And I got a chance to see how everybody's understanding on it. So last part, we talked about a general explanations about as long as we know the density distribution of electron clouds, we can written, generally speaking, the form factor for atom with respect to density of the electron clouds with respect to I is a complex number, Q is a scattering vector, R is the vector between any points in your given system. So if you have a point A and B, this will be your vector, okay? And R need to be sampled around every single point in your system. So if you have this irregular shape, you need to consider these AB. You need to consider these electrons interference. So every single pair you can sample within this particular structure need to give interference, constructive interference and destructive interference effect. And this can be generalized by that equation. So we're going to give you a few specific examples, start from simple to more complex today. How does each atom's form factor look like? Okay. So before I dive in, I want to explain two very important concepts, which likely will be on next quiz. Okay. What is something we call it a form factor, and what is a structure factor? Form, spelled as F-O-R-M, form factor, and structure factor. What's the difference? What's the similarity? So if you read the book in the chapter 2, there is a relatively good explanation of that. But let's go a little bit deeper to explain what's the difference. This is one of the main jargon people speak in the scattering field. What's your form factor for your material, etc. You have to know this to speak with someone doing a lot of scattering. So in a simple man's word, what's the form factor? Have someone read that part yet? Can someone help me? Want to give a try? I see Luke.
It's the scattering associated with a single molecule, so it's not interacting between other polymers or other molecules.
Yes, that's very good. So let's use a classroom as an example. So every single of you can imagine you're a nanoparticle. Okay, yourself including me here. Form factor speaks to about how each of us scatter, okay? Each of us. So in that regards, what is my shape and what is my electron density, distribution on my arm and legs will contribute to a scattering profile of me. And generally speaking, that's a case is true if you do scattering from a dilute solution of your polymer or dilute solution of nanoparticle. If your two particle is very far away, there's no interference from one particle to the other, then we only looking at the form factor. Okay? Form factor, use a layman's term, is the shape of individual scattering element. You can use this technique to look at the shape, size distribution of individual one, okay? So most common one is people measure in solution in very isolated states. So now structure factor, since many of you didn't heard about form factor, structure factor, I'm gonna explain directly. Structure factor, listen carefully, that describes how each individual structure sit with respect to each other. So now, structure factor doesn't concern much the shape of myself. So in this classroom, you can think about structure factor is where each individual seeds are located, which comes into most significance is the lattice spacing in a crystal, okay? It doesn't need to know what each individual atom sits at crystal coordinates. It just concerns about the distance between different lattice spacing. So in this classroom, that would represent what's the distance from this table to the next one, all these coordinates. But it doesn't care if a cat is sitting in your seat. We have 13 cats in this room, or if it's a dog, or if it's a human being, because it doesn't know what is sitting in that specific location. It's only concerns about how these are packed with respect to each other, okay? So combining structure factor and form factor, you can get a full picture of what happens in this classroom. As I mentioned, form factor concerns the shape of individual atoms. So if you know the shape of individual atoms and how they pack with respect to each other, you can get a full picture, right? So make sure you understand the difference between a form factor and a structure factor. So today and the next few days lecture, we're only going to concern about form factor because we only talk about individual atoms or moleculars or polymers. There is no neighboring chain next to it, so we just look at the shape, size, distribution. Lena, please.
So would a molecule, like a long polymer chain, would that fall into the category of a form factor or a structure factor? Because there's still spacing.
It only concerns, in this case, is form factor. Unless you're looking at multiple chains that packed in closer to each other.
Then it would be for structure.
Right.
Got it. Thank you.
Could you possibly look at the form factor and structure factor of a single polymer chain?
Typically, the structure factor is very challenging to measure for polymer just because how they crystal. You don't typically look at the lattice of a one chain to the other. You're looking at multiple positions within a chain. If you look at polymer crystals, one polymer chain spans multiple crystals. So it's a little bit tricky to answer for this, but let's assume today and for the next few days, we only look at polymer solution, dilute polymer solution.
So possibly if we had like a super high molecular weight polymer chain and it was crystallizing with itself, then you might possibly be
Yeah,
able to look
but you typically won't able to study that at all. There's better tools to do it. Yeah.
Is there a critical length scale to distinguish between the two in terms of polymer chain length?
Distinguish two, and what do these two refers?
Correct.
What do these two refers to when you say?
So I mean, the form factor is going to be more like if you think of it as a globule.
Oh, I see.
Thicker
So,
polymer chain, whereas the structure factor would be like multiple globules against each other.
no. This is a total confusion. There is no molecular weight dependent form factor or structure factor. So if you look at this classroom, let's say form factor only concerns about one individual. So the molecular weight only, let's say, correspond to the how heavy I am. If I'm gaining 100 pounds, I'm going to be bigger, but it doesn't impact how I pack with respect to another molecule in the crystal. Unless in the polymer, that's a special case. Let's come back, take one step back, looking at the inorganic salts, like sodium chloride salts. So your sodium chloride atoms will be only sitting in one lattice, right? In that case, the bigger, if you have sodium iodine, your iodine, it will be bigger than the chlorine, but it doesn't interfere the structure factor. It's only increase the shape of your form factor. So in other words, the shape I gain 100 pounds or smaller, I still sitting in my lattice, just how big individually I look.
Okay. So it's structure factor is more centralized position.
Structure factor is how you pack.
Okay.
The distance between lattice. It doesn't concern individual atoms. Okay? So let me see if I can draw it. So think about this is the sodium chloride lattice. I just draw a random cubical lattice, okay? In the three-dimensional space, you have A, B, C defines how it looks like, right? And lattice means it can be infinitely expanded. So A and B and C is defined by scattering, and that's what we call a structure factor, which defines what's the relative distance between each molecule. Form factor defines how each individual looks. If you erase every single other piece, you just leave just the one here, that's a form factor. It can be bigger or smaller, it just impacts your form factor. And we will learn a little bit detail how these convoluted with each other to give you final scattering profile. Okay, any more questions? Make sure we get this sorted out. So now, don't think about solid states. We only think about, not think about lattice yet. So don't think about you have polymer piece of film or anything like that. Just imagine you're studying a polymer dissolved in a solution. Very, very low concentration, 0.1 milligrams per ml, or 0.1% concentration. That's fairly low, right? Very dilute. So the assumption is that you have fully dissolved the polymer. It's just a coil. And next polymer coil is in New Orleans, so far away. We don't have a walkie-talkie we can talk to each other. I'm just happy with myself, left in the wilderness, on a kayak, doing some fishing. So you're just looking at concern about itself, one polymer chain. And still a polymer chain is a little bit complex. Let's take one back. In today's lecture, we're going to talk about individual atom and individual molecular. Okay? So to understand that, this function, integration of exponent I, r, dr, is basically something we call a Fourier transform. Okay, this may be more less familiar with many of you. So how many of you heard about Fourier transform? Wow, very good class. I'm so happy. How many of you know what roughly that is? Okay, we have 4 or 5, great. So maybe we start with Mike. Can I put you on the spot?
Yeah.
Maybe just chat a little bit. What is your understanding of Fourier transform?
So it's anytime you have some sort of signal in the time domain, you can Fourier transform it into a frequency domain.
Very good. Exactly. So you can. I found when I start to learn about Fourier transform, this is so confusing, but generally there's some property is very relevant. So this is something we have in the textbook, but let's use this to visualize what the Fourier transform is, okay? What I mean visualize is easy. So we talk a little bit about real space and reciprocal space. Everybody still remember that? Real space is where we live. Reciprocal space is what X-ray and photons to see. Everything is reversed in the size scale. The taller you get, the smaller length scale you get in the reverse space. So everything is flipped. An ant is stronger than an elephant. You can think about that. That's a weird word. So Fourier transform basically is a portal. You can think about a Star Wars. It's a portal. You jump into the Fourier transform. It transforms you, connects you from real space to inverse space. Okay? So that's what Fourier transform in the layman's term. And now look at here. What this trying to show you is axis and show you there's a density in one-dimensional space, 1D. Okay, we can convert to 3D just in a moment. So think about 1D. And what they basically says is this is center location 0. If this area is electron density at a finite length A, you can think about that as a piece of rods, has a certain length, but has infinite thing, but it don't have a diameter, so length. And uniform electron density as shown here. When you do a Fourier transform, this is what you will get. You will get a very simple Fourier transform of sine beta divided by beta. And beta is just generally an intensity term. So if you do Fourier transform with a constant density, you will get look at a sine, looks like sine wave, but it's a attenuated sine wave. What I mean is, if you only have sine beta, it will just go as a cycle. But because it's divided by beta, this is going to attenuate with increasing the length. It very much looks like if you throw a rock in the pond. That's where the rock is impacted at the center. You have highest intensity. Then the wavelength is the same, okay? But it's getting smaller and smaller the longer distance you travel. This is critical because this basically tells you how you should visualize yourself or any real material after being portal to inverse space. And that's what X-ray sees. I would rather slow down a little bit and explain a couple more times. Quite important concepts. Any question?
So whenever you Fourier transform from real space to reciprocal space, you'd actually see an influence of the scattering density in like a position different from the scattering density?
Almost right. X-ray detector is how we see the scattered X-ray, right? Because when X-ray hits your material, this is what it's going to do. It's going to do scatter, and it's going to have some interference effect. But when we collect the X-ray, that's why we show this particular intensity square. Intensity not square. Intensity equals to F is amplitude square of your wave. So if you take a square of this particular wave, sine beta divided by beta square, this is what you would get. all the negative wave will become positive and gonna decay, right? So X-ray detector measure intensity, which is amplitude. So that's what a detector see. That's what we can do to pull it back from inverse space to measure it in real world space, okay? So let's talk 2 more things before I get everybody to ask a couple more questions. So in real space, if I'm getting bigger and fatter, probably 10 years from now, if I'm not keeping running twice a week for 50 minutes each time, I'm going to grow twice my length. So F squared is what detector can see. Did you realize something? What happens in the Fourier transform, in the inverse space, what happened to me?
You shrunk and narrowed.
I got skinnier. Isn't that crazy? Your wave function is going to squeeze at the same amount of expansion you have, okay? Same for here. If I got skinnier in the inverse space, I'm going to spread out in the Fourier transform function. And this is the extreme case we called delta function. If you have all your intensity is squeezed at infinite tiny space, then in the Fourier transform, you will have a constant value. And this will spread as infinity. So you can think about 1. This is infinity. 1 divided by infinity will be equal to 0. Okay, so that's the transform happening here. Okay, now I'll let everybody ask more questions for real space and inverse space. Lena.
So for the change between A and C, where you're getting larger,
Yeah.
is that related to the electron density on the atom?
So
Is that
this is an example. Yes. So you can think about how do you visualize these two. This you can visualize the atom with a larger diameter. And the top you can think about atom with smaller diameter. And we're going to talk about real data, what people measured in real material. But this tells you it's interesting things in the scattering, because when you talk about inverse world, it's just everything got flipped. Any more questions for Fourier transform? Luke?
Kind of a question, more of a statement to see if I'm correct.
Sure.
So for G to H, we can think of that as more as an electron within a given atom, because that would be the smallest density that you can have, which would be represented by a line. And so each electron provides, once you take the Fourier transform, this constant value, but then it is interfered by all the other electrons in the atom, correct?
Not true. So this is just an example shows how the Fourier transform, uniqueness of Fourier transform function. It has nothing to do with, because in real case, we could never reach the case in the G, all the atom is confined with infinitely small. It's not even atom small, it's going to be even smaller, okay? So every single material going to be interfered. If you do a Fourier transform, it will look like this. And we will talk about what does atom look like, which is coming to not yet. We need to first talk about a little bit more form factor before we talk about atom. So we talked about if we do integration. So if I zoom in here, if we integrate a Fourier transform of any universal function q x, x is basically, in the previous equation we showed, x can be just a value q, right? So you can integrate it. You guys don't need to learn this in mathematically. I'll show you the answer. If you integrate everything, what you will get is a sine 1.5, a half aq, and a half aq again. So when you integrate or do Fourier transform of a real space value, this is what you get from sine you can think about this as just sine x divided by x. Okay? Any real space transformation. So how does the form factor looks like for, let's say, a given electrons? Just a one electron. Form factor is given by sine x divided by x function. And if we show what's the value of x and show what is phi, if we plot it out, at 0, you will see x behave like this. And it's almost impossible to get to 0. Remember, there you cannot divide by 0. But if it's bigger than 0, then that's kind of attenuation wave you would get. Okay? So how does it impact our understanding? Let me go here. Let me first show you a few real examples, then we can go back. So if you have a homogeneous particle, so let's say you synthesized a polymer nanoparticle, uniform in density within it, you do scattering of it, or more common cases people actually do is nanoparticle. In organic community, people make gold nanoparticles, then study it. If you have a diameter of d, you do scattering from this spherical structure. Just look at this form factor. This is given almost exactly with sine x divided by x, right? We talked about form factor. So if you do scattering from this individual gold nanoparticle, that's the scattering curve you would get, plot as intensity versus the Q. Okay? Easy? But now I'm going to ask you a little bit. If I squeeze the ball, get d smaller, how would you expect this form factor to be spread out, right? So you would have to fit first dip. If you double that, your first dip will be here, then the second will be bigger, okay? Because it's inverse relationship. In this case, you're not looking at just where the peak are or other things which typically in XRD people are looking for. In this case, you're looking at the shape and the profile of scattering. And you need to do some modeling to get what the dimension of your particles are. So now if I get my particles bigger, increase the size, then your frequency is going to be squeezed. Sound like I just squeeze on QX and pull it left and right. And you can do the same treatment to any arbitrary geometry. If you look at the nanorods, in this case, it will be slightly different. In a very large cube, you basically look in smaller size scale, which will represent to this fringe patterns as well. But on the larger scale, you're more looking at this one-dimensional lens, so it will be showing slightly different signature compared to that one. You can model all of these using a modeling software. We can talk later parts called the SAS view, or SAS view, SASVIEW. So what's the significance? What's useful? What's something you can do at preliminary data analysis is you can determine where is the dips are and use this very simple equation. Real space diameter correspond to 8.986 divided by Q. You can get what's your size scale of your nanoparticle is. It's a good first estimation, but better you fit the data. Okay? Lena, please.
Can you please just one more time describe the difference between the graph on the left and the graph on the right?
Yeah. So graph on the right, we never talked about that. Okay. So we haven't teach that yet. So we're not going to go through much. I just want to use this slide to show you what is a what is form factor? What's a fully transformed for spherical particle? Okay, so this actually almost resembles the real data you would measure. I think we did it using our instrument a couple years back for some gold nanoparticles, and we see it almost exactly like this particular pattern. So in the detector, then you would look at, you wouldn't see this because this is a Q equal to 0. You will see a ring, another ring spaced out.
Dr. Boone, one more quick question.
Sure.
For when we're talking about the particle diameter getting smaller versus getting larger, is that electron density or the number of electrons in that particle the same?
So, very good question. So, and that's very insightful question. So, there's two factors you can come in to think about that. One is how dense your particle are. Let's say on me, but made of gold, shiny. That would be nice. But I'm now going to be 20 times dense than who I am now. Then the second case would be I maintain the density, but I double my size. How does these two factors come into play in my scattering equation or question? So let's go back to the first one. As I mentioned, the scattering looks at form factor. So as long as my shape didn't change, then my scattering profile will not change. What will contribute is your contrast gets stronger because your electron density gets more. So there's more occurrence of the scattering event. What the result is you'll have much better signal. So saying nanoparticle, so this is on the relative scale, but if I have to plot a gold, that will be through the roof, then have a dip at the exactly same location because D doesn't change, but you only change the density, okay? So now increase the size but not the density, then you would change you would maintain the highest point because that's defined by 0 scattering, how dense you are. Now you would look like this because you change the size, okay? Yeah.
So can we treat this curve as form factor or curve is the real scattering signal?
This is, form factor is not real scattering signal. Okay? Form factor need to be convoluted by structure factor. So if in this case nanoparticle is so far away, you can think about it, what you measure. But if you have another nanoparticle close by, it will influence this as well. So in the case, in today's lecture, in the next 2 days lecture, we only concern dilute particles. You can think about this as a measured intensity. Okay?
Okay, so the form factor is just the shape of this curve. Determine the shape of this curve.
The form factor is shape of your particle, and any particle will give a unique scattering curve. You cannot correspond to this curve to like a given shape. You need to do some modeling, right? Because if I cover here, these two looks almost exactly the same. You need a little bit information to do back envelope calculation.
Sorry, one more question.
Yeah, please.
Is how the form factor is related to this?
How the form factor, so let's go back to here, or even 2 more slides. Do you understand where we start from? From a single electrons to more complex one, right? You get that? So in nanoparticle, we're just going to concern an atom to basically a molecule within it. It will be the same atom everywhere. There is assumption the density is uniform. In other words, if I'm again,